Hey friends, here we are looking at chapter 4. We're still in chapter 4. We're ending chapter 4 beautifully. And what's happening here is that we're going to look at one final bit of information about triangles, section 4.8, triangles and coordinate proofs. And so when we talk about coordinates, you know we're dealing with the XY axis. So a coordinate proof is basically proving things about different figures, geometric figures, by putting them on the coordinate axis and using our understanding of geometry and coordinate geometry to explain or show relationships. And I'm not even going to talk about anything else. That's just an idea of where we're going. And so I think the best way to actually figure out what's going on is to dive right in. So let's take a look at example 1. We're going to position and label a triangle. So position and label triangle MNP on the coordinate plane so that the leg MN is A units long and the leg NP is B units long. So what we would get, we would not actually have this picture here. This is the doing of the textbook authors. Actually putting this on a coordinate axis. But let's think about what we have and how we translated this into this. So if you have triangle MNP and you're told that you're going to have one leg of length A, MN of length A, one convenient way of doing that is putting it along an axis. And if you put it along an axis and call it length A, then obviously and when I say along an axis, not just along an axis, but starting at the origin, you know that if the length of this is A and this is going to be 0, then this mark or this place on the y-axis would have to be A. And similarly with NP, you would line it up along the axis, holding off on the, and they also told us it was a right triangle, so it's totally legit for us to have this right angle here. We would line it up along the x-axis so that the length, being B, would give us an ordered pair or a value right here on the axis, knowing that that's B. So this is basically the only thing that you would need to do when you were working on positioning a triangle on the axis. So the answer is there for us. Some of the tips discussed in your book are here. Step 1, use the origin as a vertex or the center of a triangle, which is really helpful as you saw in our last example. Place at least one side of the axis of the triangle on an axis. Keep the triangle within the first quadrant if possible, because that'll give us positive values, and use coordinates that make computation as simple as possible. So here in example 2, we're going to get an opportunity to play around with the idea. So here we have in example 2, we're going to identify missing coordinates. So we're going to name the missing coordinates of this isosceles triangle XYZ. So we're given that the triangle is isosceles. We are looking at the orientation. We're given that this point here is A because Z is at A something. Well, if Z is at A something and we're on the x-axis, this ordered pair should be A0, right? Because the Z point is on the x-axis, and we know things on the x-axis have a y-coordinate of 0, right? All right, so we got that one. The next one is we are recognizing that this is an isosceles triangle. So we know something about isosceles triangles. The sides are equivalent, and therefore we can think that the vertex might be directly in the middle. Let's see if we can get a little bit further on that idea. First of all, this point X is right here at 0, 0. Because it's right there at the origin. The next thing we need to do is consider the coordinates of y. When I look at y, I'm recognizing that we have a couple of things going on here. This is an isosceles triangle, and the relationship between the isosceles triangle sides is that the sides are of equal length. And this line that I'm drawing, this is something we haven't talked about, but this point should be directly in between these two endpoints. And if that's the case, then I know a little bit about this x term. This x term is directly between 0 and a. It's halfway between 0 and a. It is half of a. So the x term is half of a. A over 2 is how I'd write that. The next thing I have to figure out is what the y term would be, and I have no indication for it. So what I'm going to do is simply choose a new variable, a simple one, b. So my ordered pairs for the given shape that I have here is 0, 0 for x, a, 0 for z, a over 2, b for y. Here in example 3, we're going to write a coordinate proof showing that a line segment joining the midpoints of two sides of a triangle is parallel to the third side. So here's our figure, nicely placed on the XY coordinate system, and we're going to prove that this, let me highlight this, we're going to prove that ST is parallel to AB. So this is pretty generic. We are given that this point here is 2B, 2C, and this is the origin, which just makes life a little bit easier for us. Let me get my pen back. This is the origin, and here's B. And what I'm thinking about, honestly, is I remember from from algebra, if two lines have the same slope, if the slopes are the same, then the lines are parallel. Slope same implies parallel lines. And so what I'm thinking is, if I could figure out the coordinates of S and T, and I can show that the slopes are the same, then maybe I can say that they're parallel. Definitely I can say that they're parallel. So how can I find the coordinates of these points? Well, we were told that these are midpoints. And if they're midpoints of these segments, we know how to find the midpoint of a segment. Do you guys remember the midpoint formula? To find the midpoint, you basically take the average of the x terms, and that's going to be your new x coordinate, and then you take the average of your y terms in order to find the new y coordinate. So I'm going to let that be my thought bubble as I go through the process of figuring out what the value of s is. So s has to be, the coordinates of s have to be 0 plus 2b divided by 2, right? The average of the x terms, and then I'm going to do the average of the y terms. Now that I've done that, clearly you guys are seeing that s has to be b, c, right? 0 plus 2b is just 2b, divide that by 2 and you get b. Same thing here. So I've got bc for that, and then over here I'm going to do a similar thing. I'm going to do it kind of quickly in my head. 2b plus 2a, well, let me not. So I'm looking for t, and I'm going to do 2b plus 2a over 2. That's the average or the mean of my x terms, and I'm going to do the same thing with my y terms. This guy comes out really easy. The y coordinate is just going to be c, whereas the x coordinate is going to be b plus a. And so now time for me to find my slope. The slope of segment ST, as the slope of any line, will be the change in y over the change in x. So when I do that, I get at the top c minus c over, let's say, b plus a minus b, which leaves me with, let me get rid of some of this stuff over here, which leaves me with 0 over a, which is really just 0. And if this comes out to 0, I think I'm good. So now if I find the slope of AB, what I have is that 0 minus 0 at the top, change in y, over the change in x, 2a minus 0. And again, you see I got it. I got that that's 0. So I can now confirm that they have the same slope. Therefore, the lines are parallel. Example 4 has us talking about or looking at the Bermuda Triangle. And this is a triangle that is a space or a place that is in a region formed by Miami, Florida, San Jose, Puerto Rico, and Bermuda. The approximate coordinates of each location, respectively, are given as follows. And we can kind of use those as ordered pairs. We're going to write a coordinate proof to prove that the Bermuda Triangle is scalene. So I wonder what you're thinking. I wonder how you would do that. Now we remember scalene triangles are triangles where all the sides have different lengths. So we need to figure out the length of each of the sides. And so what we would do here, and I'm just going to tell you this, I'm not even going to go through the whole thing. What we would do here is we would take each of the segments, MB, and we would find the distance from one point to another. Yep, you got it. We're pulling out the distance formula again. BP, and we would use the distance formula to find the distance from B to P, and then finally MP, we would find the distance from M to P, and we would work that whole situation out. And with a little bit of elbow grease and perhaps calculator pushing, this is what we would get. And so by getting three distinctly different lengths, right, using our, let's keep that here, getting three distinctly different lengths by using the distance formula, we can conclude that indeed the Bermuda Triangle, because I know you were wondering, is scalene. Now that that is concluded, that is really the end of this lesson and the end of the chapter. Please let me know if there's any guidance that I can give on some of the other examples, if there's any issues, and definitely take the time to take the practice test. Let me know when you need the test and I'll send it to you. Take care, guys. Have a good one.